We're going to take a look at your conservation of momentum notes, part 2, inelastic collisions. This is on page 13 of your packet. So if you could go ahead and open that up, scroll down to page 13, and let's talk about what the difference is between inelastic and elastic collisions. So elastic is just like what it sounds like. It is when items bounce off of each other. And inelastic is when they stick. They stick together. Things come together, like if you were sitting on a skateboard and someone tossed you the medicine ball and you caught it, that would be an inelastic collision. So we're going to focus on perfectly inelastic collisions for the problems that we're taking a look at in this particular note set. So let's define that to start with. So for inelastic collisions means that some kinetic energy becomes thermal. The energy is still conserved. But if something is perfectly inelastic, it means that they stick together after the collision. So they're moving. Objects are moving to start with. Or moving at the start, I suppose you could say. So they have velocity, at least one of the objects has velocity, and they're going to stick together. After the collision. And the way that we are going to solve these inelastic problems is you're going to go ahead and find your initial momentum. You're going to find your final momentum, so the before and the after. And then you're going to set those two things equal to each other. And solve for your unknown. So let's take a look at an example problem. Scroll down. You'll see that we have a 20 kilogram medicine ball. It has a velocity of 5. And that ball is being thrown to a kid sitting on a skateboard. The child and the skateboard are not moving at first. They have a combined mass of 60. And I want to know, how fast are they going after they catch the ball? So initially, to find the initial momentum, we're going to take the momentum of the ball and we're going to add that to the momentum of the kids sitting on the skateboard. So as a reminder, momentum is mass times velocity. So to find our initial momentum, we're going to take the mass times the velocity of the ball plus the mass times the velocity of the kids sitting on the skateboard before anything is thrown or caught. So my initial momentum is going to be my 20 kilogram medicine ball times the velocity of that medicine ball, 5 meters per second, plus the mass of the kids sitting on the board, that was 60 kilograms, but the velocity was 0. So that whole side of the equation goes off to just 0, which is nice mathematically. So we're going to go ahead then and multiply that all the way through, and you come up with 100 kilogram meters per second. So that's initially what's happening. Now, after that, after they collide, I'm going to move this over a little bit, to find the final momentum, you're going to go ahead and take the mass of everything, because now the kid caught the ball. So we've got the mass of the ball, the mass of the kid, plus the mass of the skateboard. So the mass of all of it, m times v, final velocity. All right, so for that one, for P final, we're going to go ahead and take the mass of everything. So 20 kilograms plus 60 kilograms. And then we're solving for V final. So I know from conservation of momentum that P initial equals P final. Momentum is conserved. So I'm going to go ahead and use this 100 kilogram meters per second as my final momentum because it is conserved. So I can go ahead and set 100 kilogram meters per second equals 80 kilograms, 60 plus 20, times velocity final. And then we're going to divide by 80 on both sides. Cancel, cancel. And when we do that math, we get 1.25 meters per second as our final answer. So there is your complete work for the example. You started with your P initial. You found out what that was. The good part was that one thing was not moving, so part of that equation was 0. It could have been moving. We'll try one of those as well. And then for final, the key there is you want to remember if the two things came together, because it's an inelastic collision, that you got to make sure you include the mass of everything connected to find that final velocity. Okay, let's try another one. Scroll down a little bit. Okay, so now we have a train. It's moving along, and it runs into something that is also at rest, and they lock together after the collision. I want you to try this one. It is pretty much what we just solved a moment ago. You're going to start with your initial momentum, which is the train plus the boxcar. And then your final momentum is you got to make sure you get the mass of everything to get your final velocity. And the answer for final velocity, so that you can check your work, V final is 6.7 meters per second. So try this one on your own in a moment. But I want you to go ahead and scroll down to number 2 so that we can see a different one where two things now are moving instead of one thing being at rest. So we have a 140 kilogram tackler, a person, moving at 3 meters per second, and they hit head on with a 90 kilogram halfback. So they're playing football, and that person's moving at 7.5. We want to look at their mutual velocity after the collision. So this is still inelastic. It's just like the first two that we looked at. The person runs into the other person, and they tackle them. So they hang on. So the two people move off together all at once. And so again, we're going to do initial. And so for P initial, we're going to do P of the tackler. I'm going to call that T. Plus P of the halfback, I'm going to call that H. And so, again, we need to do mass times velocity of the tackler plus mass times velocity of the halfback. So we need to be a little bit careful with signs here because remember that direction matters. And if we're going to call one person moving to the right and the other person moving to the left, then we're going to have to make sure we note those signs accordingly. So our P initial then is going to be the 140 kilogram person that's going at 3 meters per second. And we're going to add that to the 90 kilogram person that's moving at 7.5 meters per second the other direction. Make sure you are paying attention to this little guy right here. That will throw you way off if that one is not the right sign. So you're going to go ahead and do that math all the way through, and we get an initial momentum of a negative 255 kilogram meters per second, which means the change in the momentum is in the direction of the halfback. So the halfback is winning, if you want to call it that. And then we want to remember in the middle that momentum is conserved. So we know that our P final is also a negative 255 kilogram meters per second. That's kind of the little in-between step that you have to think about. And then let's go ahead and take a look what's happening after they collide. We know that our P final is the mass of everybody times the velocity final. So I get negative 255 kilogram meters per second, because I just figured that out, equals the mass of everybody, which is 140 kilograms plus the 90 times velocity final. And so if you do all of that math, go ahead and do the algebra, we get a final velocity, over here so that we can see that a little bit better, of a negative 1.11 meters per second. So that means in the direction of the halfback. Okay, so there's an example where you have two things that are moving at the start, but it's still an inelastic collision. So let me give you the answers here for the rest so that you can check your work. So for number 3, our V final, I'm going to just scroll down, so I want you to jot these down, is 17.25. Try that one. For number 4, I think we're looking for V initial in this one, yeah, is 0.14 meters per second. Oh, and we're talking about Maple. That's my puppy. And then for number 5, with the dart, we have a dart going into a box. So for number 5, we have V initial. The answer for that one is 150.6 meters per second. For number 6, our V final is 6.25 meters per second. And for 7, part A, our V final is 0.102. And our V final for part B is 0.213. And we will get to these notes in the next video. See you soon.